Hello and welcome to Calculus Tutorial. We are going to continue looking at definite integrals here. So that is the area underneath a curve. And so what we've already done is we can find the area if we can use geometric shapes. So if you can take that area under the curve and split it into rectangles, triangles, circles, you can then find the area of all those and find the definite integral. But what happens when you cannot use geometric shapes? There are plenty of functions, equations, and graphs that don't have geometric shapes under them. So what do you do then? Well, we can start by doing something called a Riemann sum. That's the guy's name, Riemann, who sort of pioneered this method, and it will allow us to take the area under a curve that does not have geometric shapes. So let's start with a nice easy one here. How can you find the area underneath x squared from 0 to 3? That's what that definite integral is saying. And x squared, think of a parabola, that is not any sort of geometric shape that we have an equation for. So here is sort of a animation of how you do it. So you take x squared and you start putting rectangles in it. You start big, and as you add more and more rectangles, that shaded area becomes almost exact. And a rectangle is very easy to find the area of. The only problem with this is you can see that you need a lot of rectangles. And so when we do this method, it's mostly going to be an estimate. It's not going to be perfect, because if I made you add up all those rectangles on, say, that step, that would be a lot of work. And so I'm not going to make you do anything quite that tedious, but we are going to add some rectangles. So there are three types of rectangles that you can put into underneath a curve: a left Riemann sum, a right Riemann sum, or a midpoint sum. And let's take a look at that. All this has to do is with how the rectangles are oriented in underneath your curve. So let's draw this equation here. So 4x minus x squared looks something like this. All right, and we're going to be going from 0, and it crosses the x-axis again at 4. 2 is, of course, in the middle at the very top, and you have 1 and 3. You can check that on your calculator if you like. So, a left Riemann sum means that when I draw a rectangle up underneath this curve, the left corner of the rectangle is going to touch the curve. Okay? And that's how tall the rectangle is. The left corner touches the graph. So this next one, if I draw up, there we go, we'll come up, keep going up, touch the curve on the left corner, and then go over. This one will be touching here and going over. And the weird one is this one. This rectangle right here from 0 to 1, I need the left corner to be touching. Well, the left corner is down here at 0, and so that rectangle, it is there, but it's completely flat. That's the hardest part about this method. As you can see, we have a lot of missed space, and we have some space that goes overflowing. And so this is an estimate. It's not perfect because we're only doing 4 rectangles. And again, you can see each rectangle touches on the left. So now we have to add all of those up. So the integral from 0 to 4 of 4x minus x squared is going to be approximately equal to, the first rectangle has an area of 0. The second rectangle is going to be 1 times, let's see, so we need the y value right here. So what is the y value when you plug in 1? it will be 4 minus 1, which is 3. So 1 times 3 is 3. The next one, if you plug in 2, you get 8 minus 4, so that will be a height of 4. So it will be 1 times 4, so that area is 4. Plus, and then this area here, 1 times that one is back down to 3, and so that area will be 3 plus 3. So 3 and 3 is 6, and 4 is 10. So the area underneath that curve is approximately 10. All right. So that is a left rectangle. We now also need to take a look at right rectangles. So a right Riemann sum. Same idea, we're going to add up rectangles, but this time the right corner of the rectangle is going to be touching the curve. So what does 1 over x look like here? Draw a graph here. On the positive side, 1 over x looks something like that. And we are going from 1 to 2. I'm going to space it out a lot so I can make my rectangles look good. All right, this time I'm going to use 4 rectangles. So if I'm going between 1 and 2 and I want 4 rectangles, first we have to subdivide all of this. So that will be 1.25, 1.5, and 1.75. And as I draw my rectangle up, so here's going to be a rectangle between these 2 points. As I draw my rectangle up, the right corner, so this line here, is going to be what dictates how tall it is. So I'm going to hit the graph there and then go over. The next rectangle, the height is going to be dictated by this one. So when that one hits, I'm going to go over. And then when this one hits, I'm going to go over. And then when this one hits, I'm going to go over. All right. So as you can see now, each rectangle is touching the curve in the top right hand corner. And we have 4 rectangles, and we're going to add the area of each of those rectangles. Now, rectangle is length times width. This time, the width is 0.25. So the first one will be 0.25 times the height. Well, the height is dictated by the y value, where x is 1.25. So I need to know what the y value is when x is 1.25. This is going to be a decimal, so let's take out our calculator here to help us figure that out. Okay, so I'm going to go and type in this equation, get rid of everything else that's there. We are looking at 1 divided by x. And because I'm going to plug in a couple of values, I'm just going to go to the table and type them all in. So I don't care about the 1 actually, but I'm going to put it there anyways. And then I need 1.25. And I'm going to put 1.5. And then 1.75. And 2. So those are my values, and I'm going to put them in a table. So I have them outside the calculator. So my x's are on top here. 1, 1.25, 1.5, 1.75, and 2. And then my y values, 1, 0.8, .667 is 2/3. 0.571, I don't think that's a nice fraction. And then 0.5. Now you oftentimes see this in table form, which is why I wanted to put it on the table. So think about the rectangles now. The first rectangle goes from here to here. And the y value you use is the one on the right. The next rectangle goes from here to here. The width is again 0.25 times the height, and you use the right number. This is the right number, 2/3. Your next rectangle goes from here to here, and the height is the right number, 0.571. Our width is still 0.25, and times 0.571. And our last fourth rectangle goes from here to here, and the width is again 0.25, and the height is the right number, which is 0.5. All right, so one nice thing about a right sum, what numbers in your table do you use? You use all the right numbers and not the one on the left. And so you can hopefully guess what you would do for a left-hand sum. So now I simply have to type this into the calculator and see what number it gets me. It's a little jumbled, sorry about my handwriting there. But if you take a look, they all have a 0.25. So if I want to make my life a little easier, factor out the 0.25 in this case, and then you'll have 0.8 plus 2/3 plus 0.571 plus 0.5. That will be a little easier to type into the calculator than all the multiplications at once. So let's do that here. So 0.2, oh, not right there though. Let's see here. Sorry about that. Calculator wasn't doing what I wanted to. All right, so now we're going to do 0.25 times 0.8 plus 2/3 plus 0.571 plus 0.5. All those up, hit enter. We get 0.634. Oops, sorry about that. So this integral, I'll write the whole thing. The integral from 1 to 2 of 1 over x is approximately equal to forgot what it was, 634. All right, there we go. So we used 4 rectangles there to find that. A little tedious. Oftentimes, that's a little more work than you have to do. All right, one more quick one to look at. We did left sums, we did right sums. Now it's time to take a look at the midpoint. Same idea, we're still going to be using rectangles, only instead of using the left or the right hand corner, we are going to be using the middle of the rectangle. So this time, you often see this when you don't have a function, or sorry, an actual equation, just a table. And so here's a function f of x. We have a couple of points, y values for it. We don't actually have the equation. Using 3 rectangles and a midpoint sum, what is the value of this integral from -2 to 10? All right, and so here we just have to do with what we've got. We can't actually do these rectangles the way we want to. We have to do the way we're told. So if I'm going to go from -2 to 10 and divide that into 3 rectangles, one is going to go from here to here, then from here to here, and then from here to here. That gives me 3 rectangles. And so take a look at this rectangle. How wide is this rectangle? Well, from -2 to 1 is 3 times the height. How wide is this rectangle? Well, from 1 to 5 is going to be 4. How wide is this rectangle? From 5 to 10, it is 5. So the rectangles aren't even equal widths, but we did what we could with the table. Now, how tall are these rectangles? Well, because we're using the midpoint, the height is going to be the middle number. So our middle number is 8, our middle number is 0, and our middle number is -6. So this integral will be approximately equal to 24 plus 0 minus 30. So it looks like -6. All right, so using the table, we had to use the width of the rectangle that they gave us, and then the height was the middle number, because we were doing a midpoint. All right, so those are sort of the 3 ways you can estimate a definite integral if you can't use geometric shapes. There will be a better way next time.